For our next talk, we have Cleto Miranda-Neto from Universidade Federal de Paraíba, and he's going to talk about differential ideals and homological problems about derivation models. Thank you, Cleto. Please go ahead.
Okay, thank you, Luis. I'd like, first of all, to thank Luis and Jack for the very kind invitation to be part of this nice event, MCA, Buenos Aires. Okay, so time flies. Let me explain shortly that the goal of this talk is essentially twofold, in the sense that the first part we study maximally differential ideals, okay, and focusing on generalizing a couple of theorems due to Maloo, Alok K. Maloo, it's an Indian mathematician. In the second part, I will discuss about homological problems about derivation models, okay, especially generalizations of classical world conjectures involving this model, right? So this first part is quite basic, so I'm not going to spend a lot of time here. By ring, we mean, as usual, a Noetherian commutative ring with 1, right? And you fix a ring extension like this, okay? So K is completely general, it's a subring. I'm assuming for simplicity that K is contained physically in R, right? So derivation, by the way, I'm aware that some of you guys have been working with P derivation, a more elaborated concept, while I'm still stepping on a truly safe land of standard classical derivation, right? So I won't take the risk by now. So derivation for me is the derivation in the usual sense. I mean, an additive map satisfying product rule, Leibniz rule. And these objects can be collected in a module, and then you have this submodule, which is formed by the derivations vanishing on K, right? Okay. So there's another basic concept, which is that of, if you fix an unempty subset D of the derivation model, then an ideal I of R is said to be differential, D differential, if it is invariant under every derivation line in D. I'm sorry, here, I'm sorry. Here is not the derivation model, it's D, okay? Here is not the derivation model, sorry. It's invariant under every derivation line here in this subset, okay? So you can consider the family, in fact, a partially ordered set consisting of all proper D differential ideals of R. And of course, the zero ideal lies there, okay? So there's a maximal element. So this is the first observation. The second one is that if you assume that R is local, then it can be shown that for a given D, there's a unique such maximal element. Then you can define the following notion. A maximal element of this pole set is called a maximally D differential ideal of R. And then you say that, I mean, this P is like a Gothic P, okay? This stands for maximally differential ideals. So you say that P is a maximally differential ideal simply if it is the maximally differential, the maximally D differential ideal for some D, for some subset D of the derivation model, okay? These are standard notions. If R is local, then as remarked above, you can say that P is the maximally D differential ideal for a given D, okay? There is uniqueness. And just for completeness, I'd like to mention that in case P is 0, okay, if the maximally D differential ideal of R is the zero ideal, then you say that R is this simple, which is a classical object, I mean, highly investigated. So in this sense, this concept generalizes because you don't want P to be necessarily 0. Okay, fix a local ring, a D as before, and P stand for the maximally D differential ideal. So let me recall a couple of well-known facts. First, some facts proved by Lequin long time ago, which are these ones, okay? Depending on the residual characteristic, if it's positive or if it's 0, then we have respectively that the P is M primary or prime. Okay, these are standard facts. The second one is due to Maloo. In case R contains a field, in case D is a submodule, finitely generated, closed under Lie brackets, then this guy here, the tensor product is free as a module over R mod P. This shows in particular that if R is this simple, then D is free. This is an interesting fact, okay? particular for D equals to the entire derivation module. So in order to make things a little bit more concrete, let me give some examples. You fix n an integer, p prime, blah, 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 and you consider this local ring here, okay? Z of x1, x1 localized at this maximal ideal here. If you consider D as being the set, unitary set consisting only of this partial derivative with respect to the first variable, then in this case you get P as being this ideal here. Okay, so note that you raise x1 to the pth power. Another example is this one, a local ring, regular local ring. Both are regular local rings, of course. Here you have a characteristic P case, and we're going to take D as being this set of derivations here until the pth variable. Okay, P is at most D. So in this case, you have this maximally D differential ideal here. Now let us.
Sorry to interrupt. I think there was a question about 2 slides ago.
Okay.
Karen was, Karen was asking free in what category?
What do you mean D is free? Isn't D just a set of derivations? What does it mean that a set of derivations is free?
No, by hypothesis, the theorem of Malou, D is a submodule.
Oh, so D is a submodule, and you mean it's free as an R module?
Yeah, yes, it's an R module. I'm sorry, over R, yes. I mean, for the general theory, D is just a non-empty subset. But if for this result specifically, this is an R submodule, yes. So for an example, over a non-regular ring, we have this hypersurface local ring. If you take D as being this set consisting of this partial derivative with respect to X, then you have P like this, generated by Y and Z, okay? And for a non-regular example, in characteristic 0, we have this hypersurface ring here. And if you consider D as being the entire derivation module, then you have this P, generated by X, Y, and Z, okay? So you may wonder why W is not there. And the reason is that if you consider this delta, this derivation, you can see easily that this derivation kills the polynomial, right? Then it induces a derivation of R, and then it sends W to 1. So the maximum ideal is not differential. Okay, so the maximally D differential ideal with respect to entire derivation module generated by X, Y, and Z. Is everything okay, Jack? Okay, the next 2 results, let's assume that R is a local K domain, blah, 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 the beautiful setting, and P denotes as before a maximally differential ideal of R with respect to the entire model of K derivations, right? So the first theorem due to Malou is the following. He assumes that the height of P is at most 2, which is of course automatic if, for example, the dimension of R is at most 2. Then R being regular implies this module to be free as an R module, as usual, right? R is a ground ring. Okay, so he proved this theorem. And then 20 years later, jointly with Thiago Souza, we proved that if you replace this condition here, R being regular, okay, we don't need all finite modules to have finite projective dimension. It suffices to test the projective dimension of the derivation model itself. If it is finite, then the derivation model is free, provided that the grade of P is equal to the height of P, and again, at most 2, okay? So note that this equality here is hidden in the previous theorem, because a regular ring, of course, satisfies this equality for every ideal. I mean, any Quine-Macaulay local ring satisfies this equality for every ideal. Grade equals height. So the key point is being at most 2, and in general, for this theorem, we need this equality. It's also worth mentioning that there are some cases where we can eliminate this hypothesis. I'm not saying that this follows automatically, but it's not needed. For instance, if R has prime characteristic, okay, we don't need this equality as a condition, or if clearly if R is square Macaulay, or if R is a factorial domain, we don't need this equality. Just to mention some cases where this equality can be dropped. Okay, next. R is a local ring, P is again a maximally differential ideal. Okay, there's another theorem by Malou, which asserts that if R is regular, then P is a complete intersection. Now it comes to the question as to when P is generated by a regular sequence, okay? So Malou has this theorem, 2006. And before going to our generalization of the second Malou's theorem, I'd like to point out that the converse of Malou's theorem is not true. You revisit that example, okay, I mentioned some minutes ago, this surface ring, case a field of characteristics P, and you take this D, and P is this ideal, remember, Y and Z. So clearly it has height 2, hence a complete intersection, while of course R is a singularity. So the converse does not hold. But you have this correction here. We don't have to assume that all finite models have finite projective dimension. It suffices to assume that P itself has finite projective dimension in order to get this implication, hence also the converse. This is of course a characterization because a regular sequence is resolved by the causal complex. Okay, this closes, say, the first part of the talk. Okay, so we'll be still interested in considering freeness of derivation models, or I mean, it's finiteness of its projective dimension, but no longer involving the maximally differential ideals. Okay, that's the difference between the first and second parts. So now we raise again this driving question: when is the derivation model free over R? Okay. Of course, this is possible, as everybody knows. I mean, if you have a polynomial ring, then model of derivations is free on the partial derivatives. If you have a complex affine algebraic variety, and the local ring of it at a non-singular point has a free derivation model, and so on. This is well known. On the other hand, not always the model of derivations is free, of course. You may consider this normal crossing divisor, and the derivation model of the hypersurface ring is in fact minimally generated by these n derivations here, okay? So what happens here is that this model is no longer free. Why? Because it's minimally generated by n elements, but its generic rank is n minus 1. So these two numbers don't agree, so it cannot be free. Okay? Well, must R be regular in order for its derivation model to be free? No. Certain non-regular local rings have a free model of derivations. The first example is quite obvious. By the way, I wrote the exponents here and the characteristic. Okay, so the partial derivatives themselves of the variables give you a free basis of the model. But this next example is more interesting. I suppose case a field of characteristic P, at least, P, positive characteristic, and consider this three-dimensional complete intersection local ring. In this case, the model of derivations is free. Okay, a basis being formed by these three derivations here. Okay, of course, if you consider the first equation, then you have the power series ring only three variables model of the first equation, then you still have this property, the derivation model is free, basis being these first two guys here. But I just wanted to illustrate that this is also possible for higher codimensional complete intersections. And this can be even extended to higher codimension, not necessarily to the codimension of the complete intersection. Let me speak a bit about one recent criterion that we have obtained jointly with Jorge Perez this year. Remember, we are looking for conditions under which the model of derivations is free, and consider this quite general context where R is a local K algebra, K is not assumed to be a field necessarily, and has positive depth, and finite generated, blah, blah, blah. Now, suppose the standing hypothesis is this one. Suppose there exists a torsionless module, non-zero module U, okay? I mean, torsionless means, of course, a syzygy module, okay? Such that the depth of this tensor product is not the depth of U minus 1. So this is a subtle condition, which, if you think, touches a very hot topic in commutative algebra nowadays, which is the tensor product of modulus, and especially its depth has been investigated by many authors recently. So, okay, under this condition, and in addition, any one of the following conditions, namely this second tau here vanishes, third tau, fourth tau here vanishes, and or R is a complete intersection and this second diagonal X here vanishes. Then in any of these cases, there is free as an R module, right? Okay, let me speak quickly about classical conjectures and results. Henceforth, we shall consider this setting, okay, in order to make things more concrete. And this is classical setting of classical conjectures, well-known conjectures. So S is a localization of polynomial ring like this. I is a non-zero proper radical ideal. And of course, in this context, if I is regular, then it's well known by the Jacobian criterion that the model of derivations is free. This is because the derivation model is the dual of the model of Cayley differentials. So this is clear. If R is regular, then the model of derivations is free. And the problem raised by Zariski and Lippmann in the mid-60s is, does the converse hold? So this was, by the way, the topic of Lippmann's PhD thesis under Zariski. So Lippmann gave this answer partially. I mean, he was able to prove that under this hypothesis, R is at least a normal domain. In particular, Lippmann settled affirmatively the case of curves, right? Okay. So this problem is interesting. Let me also point out that some years ago, Malou, the same Malou I was speaking about, gave an example. This is very interesting, of a non-regular one-dimensional local domain containing a field containing the rationals with a free derivation model. So, oops, do we have a counterexample? No, because S is not in the right category. Well, this is a brief chronology of the known results of the Zariski-Lippmann conjecture: curves, hypersurfaces, the graded case, dimension at least 3 in complete intersections. I mean, the classical, the standard Zariski-Lippmann conjecture, the one I stated. So the critical remaining open case is that of arithmetically Gorenstein surfaces. Now, let me state a few other conjectures, I mean, more general ones, and also results. I mean, 7 years after Lippmann proved his theorem, Shea and Storch proved this more general one. If the projective dimension of the derivation model is finite, then R is a normal domain. So this, of course, generalizes Lippmann's theorem. And you have these next conjectures here. Vasconcelos' conjecture, he predicted that under this hypothesis, R is a complete intersection. And then, I mean, this is not very well established, but independently, as far as I know, Herzog and Vasconcelos raised this conjecture between the mid-80s and early 90s as to whether, I mean, the finiteness of PD of there implies the freeness of the derivation model. Okay, this has been known as the Herzog-Vasconcelos conjecture. It's very interesting, and it's kind of a homological version of the Zariski-Lippmann conjecture. And then you can combine both and get the so-called strong Zariski-Lippmann conjecture, right? Which then predicts that if the projective dimension of the derivation model is finite, then the ring is regular. And this is hard, okay? Let me mention that the major case where this strong Zariski-Lippmann conjecture is known to be true is due to Herzog himself and Marcinkovsky. They settled the case of quasi-homogeneous complete intersections with at most isolated singularities. Next, we have this, you know, kind of contribution to this problem, jointly again with Jorge Perez, we got this result. But in depth 3, right? This result by Herzog Marcinkovsky is not in depth 3, but this one is. So in depth 3, okay, not necessarily Cohen-Macaulay, but assume that R has at most an isolated singularity, suppose any of the following conditions. R is Cohen-Macaulay, and again, the depth of this tensor product, but here, U, that big U, is this specific module here, which is the canonical module of R. So this depth is not 2, or that is an ideal way with co-depth 0, okay, such that the tensor product with the derivation model is torsionless. So in either case, the strong Zariski-Lippmann conjecture holds. Now let's look forward, I mean, generalize the strong Zariski-Lippmann conjecture. So I'm going to recall now a couple of important variants that refine the usual projective dimension. The first one is the Gorenstein dimension, okay, GDIM, which is due to Aslan and Bridge. It dates back to the late 60s. This is the minimum length of a resolution of M by totally reflexive modulus. I mean, totally reflexive module is just a reflexive module, which is moreover a module satisfying these vanishing conditions here. It's cohomology here, vanish. X of T itself against R and X of its dual against R is 0 for all I greater than or equal to 1. Okay? So this is totally reflexive. Clearly, then, a generalization of the concept of projective module. So that's why Gorenstein dimension, in fact, refines the concept of projective dimension. So, okay, now let us consider the second homological dimension called complete intersection dimension, okay, CIDIM, due to Avramov, Gashov, and Pieva from 1997. This is the infimum of the quantities, I mean, projective dimension of this guy over Q minus this guy, okay, over all deformations Q of faithful flat extensions R prime of R, okay. This data is the so-called quasi-deformation. I mean, you have a faithful flat extension of R, and then you take a deformation of a faithful flat extension. This means that R prime is isomorphic to Q modulo a regular sequence. The length of this regular sequence is by definition the codimension of the quasi-deformation. This is just terminology. Anyway, this is a quantity, and it's defined in terms of projective dimension anyway, but over a different ring, over Q. Our striking fact is this inequalities here. Okay, so G dimension is quite old. It's is known to refine the projective dimension, but then this number appeared and is intermediate between the two first ones. So this happens, and whenever one of them is finite, you have equalities to the left. Moreover, these dimensions are very well behaved with respect. I mean, there are Auslander, Brooks-Bound type formulas for both of them. There are, you know, the maximum ideal is a test model for testing both properties, Gorenstein complete intersection, and so the theory runs completely in parallel to the one that holds for, I mean, projective dimension versus regular rings. All right, these are beautiful stuff. So, okay. So in view of all of these, in the same paper where I proved a generalization of the second Malus theorem, I proposed these two problems here, which particularly in this talk I called G conjecture and CI conjecture, which are these problems. Okay, so if the G dimension of their derivation model is finite, then R is Gorenstein, and if the CI dimension of the derivation model is finite, then R is a complete intersection. Well, I mean, the pioneering idea, of course, of relating homological algebra, I mean, projective dimension, this homological invariant with ring theoretical properties such as being regular is, of course, due to Zariski and Lippmann. So I just adapted that idea to propose these problems. Okay, so of course, the root of this thing is the old conjectures by Zariski, Lippmann, and Hazel Vasconcelos. So my intention, my very first intention when I proposed these problems is, they are recent, is just to draw the attention of researchers, because it's kind of a mix of two interesting topics in algebra, I believe. One concerns the model of derivations, which is a classical object in algebra and in geometry. And on the other hand, you have, you know, these homological dimensions, sometimes very abstract. So I decided to put them together in the same context, like an overlapping context, and ask these questions. So we have some nice consequences here that I wrote here as a note. First, because this bound happens, okay, always, the CI conjecture is easily seen to imply the Vasconcelos conjecture and this Zariski-Lippmann conjecture, the classical one. Okay, this is easy to see. I made it to see. Moreover, if you are able, if you assume the validity of the CI conjecture.
We are out of time. You think you can conclude a bit in the next minute?
Okay, right. Thank you. if you assume the validity of the CI conjecture, then the strongest Zariski-Lippmann conjecture can be proved for complete intersections in order to imply the general case. So this is a bonus. Anyway, in a recent paper, Moshen Ashgazadeh proved the CI conjecture, okay, in case I is graded Cohen-Macaulay of minimum multiplicity, and gave counterexample for the case of positive characteristic. These are the main references, okay, I've used, okay. This survey by Herzog collects all of these conjectures and many interesting good stuff, and the other papers where we obtained our results. This is to the memory of Professor Vomer Vasconcelos, who sadly passed away a few weeks ago. Thank you very much for your attention.
Let's thank Cleto. Okay, I think we have time for one quick question. Okay, well, maybe I ask you one question. You think that some of these conjectures or results can be done if you take instead of derivation like higher order differentials, like
I don't know. I haven't.
Two, something like that, or like even like all the ring of differential operators, like some sort of like Nakai style conjecture.
Yeah, Nakai. Yeah. I mean, that's a good question, but I dared to call these problems conjecture, so I didn't want to take the risk to state more general, things. But of course, it's valid to consider these questions as well. Yeah, thank you.
Okay, well, let's thank Cleto again.